So in section 7.3, we are working with inverse trigonometric functions. And what is kind of a bummer is that if we were doing this unit in class and if we had more time, we could actually go through and do a proof of all of these. And it's not as hard as it seems initially, but we're going to just do a proof of one of these, and I'm going to stick to the proof that's in our notes. So recall from geometry and or your experience in trigonometry or in honors Algebra 2 that we remember that saying the arc sine of x, that's the same as saying the inverse sine of x. They both really mean the same thing. It's just two different ways of writing them. Just like we can express y prime as dy dx as well. So when we say the arc sine, just remember that's the same as the inverse sine. You might have noticed on all of our mini mock AP tests in class that on the exam it says that the inverse sine can be written either of these ways. And it's true that sometimes they go back and forth with how they express it. So we want to be comfortable with both. Okay, that was my aside. So let's actually work through this example, and I know it's written out, but it's hard to follow if you have never done this before. So let's say that y is the arc sine or the inverse sine of x, since we are working with inverse trig functions. All right, so if our goal is to find y prime, well, we can't just jump straight to y prime if we don't have a rule yet for the arc sine. So we're actually trying to derive that rule. We do know the derivative of the sine of x, or the sine of any junk, so to speak. So when I take the derivative of the sine of x, I know that is the cosine of x. So something that we could do here to get rid of the arc sine of x is we could take the sine of both sides of this equation. So remember that sine and arc sine are inverse functions. And just like every other inverse pair of inverse functions or inverse operations that we learn about, they undo each other. So the way that we get from the first line to the second line in this little proof is that we take the sine of both sides. So now we have a statement that the sine of y is equal to x. And that just has to be true. Like, that's what the inverse sine is. I guess we could have gone the other algebra route where we could switch the x and y and solve, but this is the route that I took, taking the sine of both sides. Okay, so now we can take the derivative of both sides with respect to x. We want to be careful because when we do that, we are doing implicit differentiation. So the sine of y, well, the derivative of the sine of some junk is the cosine of the junk times the derivative of the junk. So we get cosine y times y prime. The derivative of x with respect to x is 1. And then we could divide both sides of this equation by the cosine of y. So we get that y prime is 1 over the cosine of y, and we know that's the same as the secant of y. So our problem is that we really want to write this in terms of x, not in terms of y. So we can use a reference triangle that models this relationship. So it's a bummer that this one's already drawn out for us in our notes. I wish it wasn't. But let's just think this through. Let's think about what it means that y equals the inverse sine of x, or more easily, let's go back to the second equation. The sine of y equals x. So we know in right triangle trigonometry, when we take the sine of something, that something is an angle. Or we could remember that when we take the arc sine of something, we're taking the arc sine of the opposite leg over the hypotenuse, and that gives us an angle. So y is an angle, and x represents either a side where the hypotenuse is 1, or it could be like the ratio of two sides. But to simplify this, we're going to just make x the opposite side. So if you look at this drawing, like we would start with a right triangle and we would just pick an angle, either non-right angle, and name it y. So if it is true that the sine of y equals x, and we remember from like SOHCAHTOA way back in Geo, that from SOHCAHTOA we know sine is the ratio of the opposite side to the hypotenuse. So for the statement the sine of y equals x to be true, we could think of that as x over 1. So x is the side that is opposite, or the leg that is opposite angle y, and 1 is our hypotenuse. So as you're looking at this labeled triangle, you're like, well, where'd that other leg come from? Well, unless you read the text right above it, then you know that it comes from the Pythagorean theorem. So if we don't know what this leg is yet, we know from the Pythagorean theorem, a squared plus b squared equals c squared, or c squared minus b squared gives us a squared. So 1 squared minus 1 being the hypotenuse, x squared, one of the legs, gives us the other leg, I'm just going to call it right now, a squared. So since 1 squared is just 1, this leg that we're trying to solve, we're going to pretend that the answer is not written on the picture for us, is 1 minus x squared. And so we would take the square root of both sides here, and we would get that a is going to be just the positive square root of 1 minus x squared. We're not interested in a triangle having a negative side length. So that's where that comes from. So we go to this reference triangle to be able to do that. So now if we go back to our derivative, this reference triangle, this is what relates x and y. And again, we got it from really either of these first two statements. For my brain, it's easier to think of the sine of y equals x, but this also illustrates that y is the inverse sine of x, or the arc sine of x. So if our goal is to rewrite this derivative in terms of x, then we just figure out from this triangle what is the secant of y. And this kind of actually helps me to go back to thinking of this as 1 over the cosine of y. And I think that's just because I teach geometry and not college trig. So if I'm looking at my reference triangle, the cosine of y is going to be the adjacent side of the triangle over the hypotenuse. So according to our triangle, the cosine of y is the square root of 1 minus x squared over 1. And since the secant of y is the reciprocal, the multiplicative reciprocal of the cosine of y, then that means the secant of y is 1 over the square root of 1 minus x squared. Therefore, the derivative of the arc sine of x is 1 over the square root of 1 minus x squared. And if we didn't have like a funky weird year, we might spend more time here because I think it's really interesting. But no matter what, no matter how many years I've taught this, no matter how much time we have to spend on this in the classroom, you never want to find yourself on any exam deriving a formula that you could have memorized just because it takes up valuable time. If you have time left over, it's a great way to check. So what I would recommend to you is that you memorize, again, everything that's in this box. So we derived the first one, excuse me. And if we had more time, we could derive them all, excuse me again. So we don't have more time and we're not going to derive them all. But if that's something you want to try, I'd be happy to check your work for you. So what I recommend is memorizing the ones on the left and connecting those to the ones on the right, because some really familiar stuff happens here that relates to our derivative rules of trig functions. So we already dealt with the arc sine of x, and we got 1 over the square root of 1 minus x squared. So if you remember the relationship between the derivative of sine of x and cosine of x, it's only different by a -1. Well, lucky for us that the same relationship is true here, that when we take the derivative of the cofunction, so the cosine, we have a -1 on top, and that's the only difference. The only difference is it's negative. So if we look at the secant, the derivative of the arcsecant of x, or the inverse secant of x, is 1 over the absolute value of x times the square root of x squared minus 1. And again, we just want to memorize that. If you're wondering about the absolute value, that just has to do with domain restrictions on secant. And then if we generalize the cosecant, so again, when we take the derivative of the cofunction, it's going to be the same as the function, but negative. So the arc cosecant is going to be the derivative of the arcsecant, but it is negative. And then lastly, the arctangent is my favorite because it's, I usually memorize this one in sine, and then I just, I don't know, I just have to think real hard about that arcsecant. These aren't fun to memorize, but I like the tangent one because there's no square root. It's just 1 over 1 plus x squared. So the cotangent is just a -1 over 1 plus x squared. So again, these are the derivatives of inverse trig functions. Okay, so there are 5 examples. What I would say is pause the video. I'm going to work them all out off screen and just kind of talk through them. Pause the video and try them for yourself first. All right, let's check our work on these. So the thing we really got to watch out for is the chain rule. It'll get us every time. So when we take the derivative of the arcsine of 5x, it's going to be 1 over the square root of 1 minus the junk squared. So that 5x squared becomes 25x squared times the derivative of the junk, which is just 5. So for our final answer, we get 5 over the square root of 1 minus 25x squared. Arctangent of 3x squared. So we know our rule for arctan is 1 over 1 plus the junk squared. So in this case, our junk is that 3x squared. So 1 over 1 plus 3x squared squared times the derivative of 3x squared, which is 6x. So again, that 6x just comes in from the chain rule. And then we could just rewrite that. We can distribute that exponent 2 over multiplication. So we get 3 squared times x squared squared, which is 9x to the 4th. So here is our final answer. The third example, so again, it's arcsine 1 over the square root of 1 minus the junk squared. When we write the natural log of x squared, just like we do with sine and cosine, you'll often see it written like that. So don't let it throw you off that I wrote it like that. That is the natural log of x squared. Again, the chain rule, whoops, because that's the natural log and not just an x. The chain rule is going to give us that times 1 over x. And we could just do this quick rewrite, 1 over x times the square root of 1 minus the natural log of x squared. All right, these last 2 examples before we get into the integration, some of the tough stuff, man, we just really got to memorize and watch out. The one at the top of page 101, there is another way we could write this. I don't think it's worth the time we have to go into it, but we could expand this binomial, and I think it actually works out that we get a factor of 4 in the square root function, which we could take out of the square root function as a 2 and cancel the 2 on top. I'm going to be honest, I just don't think that's worth our time to go there, but if you want to try that and check with me, I'm happy to go over it with you. The last example, arctan of e to the 2x, so 1 over 1 plus the junk squared times the derivative of the junk. Be careful taking the derivative of the junk, e to the 2x, that derivative is e to the 2x times 2. So this is like a triple chain rule on an inverse trig derivative. You would think I wouldn't be so cruel to you at the end of the year, but hey, this is optional. So 2e to the 2x, I shouldn't say that. I'm probably going to want to use this video in a year where it's not optional. So if you're in the future, this was mandatory. 2e to the 2x over 1 plus e to the 4x power. All right, in the next video, I'm going to get into integration with inverse trig functions. Is it as fun as it looks? You betcha.